Everybody, and welcome to ECE 42. I'm glad all are safe and healthy. Okay, let's continue our discussion from last time. We started talking about CMOS inverter. Clear? We found out first of all that the resistively loaded inverter was not what? Was not efficient because it results in what? Power dissipation when the input is what? When the input is low. Did you follow me or not? It results in power dissipation. Let's see this one here, understand what do we do. Remember, by the way, in the resistive loaded CMOS, the load line was a what? Straight line. Remember the straight line? Mm-hmm. This one is not going to be a straight line. Let's understand. I replace the resistor by a what? By a PMOS. That's a PMOS replacing the resistor. I'm going to assume that this is the driver transistor, and this is the what? This is the load.
What does it mean when that's the driver and those?
This one is going to supply this one. In other words, this one, if you replace this resistor by this, you can assume that this is the load. Clear? Oh, by the way, you can do it also the other way around. You can assume that because the input is applied to both of them. You follow me or not? You can apply the input, you can assume this is the driver and this is the what? This is the load. Clear? Just the opposite. Clear so far? Oh, good. Now, what is the first thing to do? The first thing to do is to what? Is to look at each one of them separately. The NMOS. Let's see if it rings a bell. What do we have here? VDSN, which is what? Which is the voltage from the drain to the source. That's the same as what? V9. Did you get it or not? This one is ID, which is what? Which direction? Down. Clear? Okay, good. And when are these? VGSN, which is what? Which is the same as the input. Clear so far? Oh. And one more time. How many modes do we have? We have 3 modes. What do we call this? Saturation mode. What do we call this? Trial mode. What do we call underneath this? Current mode. Did you get it or not? Now remember, VGSN, which is the input, has to be what? Greater than the threshold for the NMOS to turn what? Or to turn on. Clear so far? PMOS. What do you notice? Everything is in negative. The VDSP is, where is VDSP, by the way? Where is VDSP? Is the voltage between the what? The drain and the what? Source. So why is this one negative? Because in a PMOS, the source is the what? Highest voltage. So when we say the drain voltage minus the source voltage, the answer will be in what? Negative. Do you agree or not? Yes or no? Good. Now, VDSP. IDP. Opposite to IDN? Opposite to IDN. This is a PMOS. Clear so far? Okay, good. What are these? VGSP. Where is it? Show it to me. Is the voltage between this point and this point? Yes? Mm-hmm. Is it also negative? Yes. Why? Because the source is the what? Is the highest voltage in the structure of the PMOS. Do you follow me or not? Yeah. What are these? VGSP. Everything is negative. So for example, this, just an example, this one, minus 6 volts, minus 5, minus 4, minus 3. Did you get it or not? And VTP. VTP is also what? Negative. Clear so far? What is the condition for the PMOS to be on? Exactly similar to this one, but absolute value. So what do I say? For the PMOS, to be on, absolute value of what? V, G, S, P, V, it's not R. Has to be greater than what? Absolute value of what? VDD. Clear? Clear? Everything is absolute value. Why? Because it's negative. By the way, all the equations for the PMOS and the NMOS are identical. The only difference is what? In the PMOS, you need to put what? Absolute value, because everything is negative. Clear? Okay, good. Where is the saturation region here? PMOS. This one, the triode, this one, the cutoff, this one. Did you get it or not? And again, as you move this way, what does VGSP become? Become more negative or more positive? More negative. So if this again, if this one's -6, -5, -4, -3, -2, and so on. Clear so far? Yes or no?
Yes.
Okay. The PMOS is a lot, which means what? Somehow I need to take this characteristic and superimpose it on top of this one. Did you get it or not? Because that's what the load line is. Load line is what? On top of the one? Of the IV characteristics. Clear? Which means what? What does that mean? It means the axis needs to be the same. Did you get it or not? So let's see. What is the axis here? IDN. What is the axis here? IDP. Clear? I need to change this into what? IDN. Clear? But what is the relationship between IDP and IDN? Opposite. So what do I say? IDP is equal to what? Minus IDN. Or let's write IDN. IDN. Clear? One is going this way, the other one is going that way. Clear so far? So what do I need to do to these curves? I need to what? I need to flip them, hold them like this. So what do they become? Clear so far? No response. Clear so far? Good. Now, am I done? No, I'm not done. Why? What is this one? VDSP, which is negative. Keep that in mind. What is this one? VDSN. Somehow, I need to write what? VDSN in terms of what? VGSP, so that I change this scale to this one. Yes? Let's see. Where is the VDSN? Is the voltage between this one and this one? Yes?
Yeah.
Where is VDSP? Is the voltage between this one and this one?
Yep.
Yes or no?
Yes.
So what can I say? VDSN is equal to what?
VDSP
VDD
plus VD
plus VDSP. Question, why plus?
Because the VDSP.
No, what I'm saying is that could VDSN be more than VDD?
No.
Is it why? But here it shows you that you can. Plus, you have to remember this is what? Negative. Did you get it or not? Yes or no?
Yes.
No response. Yes or no?
Yes.
Okay, so from here to here is how much? VDD. From here to here is how much? VDSN. Yes? Where's VDSP is from where to where? Here to here. VDSP is this one to this one, opposite direction. Did you get it or not? But it's negative. You follow me?
Yes.
Yes or no?
Yes.
Good. What do I need to do with this character shifted? Shifted by how much? VDD. Where is this point here? 0. When you shifted VDD, how much become? VDD. So the curve becomes like this. And so on and so forth. Did you get it or not? No response. Did you get it or not?
Yes.
That the red one is for the what? For the PMOS. The blue one is for the what? NMOS. By the way, is it straight line? Is this a straight line? No. Why? Is this a linear device or non-linear?
Non-linear.
When it was resistor, was it straight line?
Yes.
Why? Because the resistor is a what? Linear device. Did you get it or not? Yes or no?
Yes.
Okay. Now let's understand, after we understand this, let's understand the behavior. Before we get to the behavior in all points, remember, by the way, the goal is to come up with, everybody got a copy of this?
Yep.
Everybody? Thank you. You're welcome. What happened to my class? How come it's shrunk? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I have 30 students.
Traffic's
20
really
in the
bad
class.
today.
Huh?
The traffic's really bad today.
What the traffic?
It's
Huh,
really
the
bad.
traffic was bad.
Yeah.
Okay, this is the goal. To find what, by the way, does it look like an inverter? Huh? Does it look like an inverter? Yeah. Now, by the way, I want you to see the transition region. Before I show you how do we get this, look at the transition region. Is it sharp?
Yeah.
Or the other one like slow? This one is sharp. Did you get it or not? Clear so far?
Clear.
Huh? Question? Clear? Oh, let's see how we get this. Let's try, first of all, let's try the extreme points. What are the extreme points? Remember, by the way, what am I changing? I'm changing the what? The input voltage. Did you get it or not? Yes or no? I am changing the input voltage, which is what? VGSN. Clear? What are the extreme? The extreme, case one, VGSN equal to 0, VI equal to what? 0. And the other extreme is what?
BD.
VI equal to VGSN equal to what? VDD. Did you follow me or not?
Yes.
No response. Yes or no?
Yes.
Let's start with what? These extreme points. I ended up, I have to use a new one. All of these are dead. Dead on arrival. They give me dead stuff.
You mean the ink is empty?
Huh?
You mean the ink is empty?
Yes. I thought I can save this till next week. I cannot. I cannot see it myself. If I cannot see it. No, this one is not erasable.
This one, yeah, it is.
They are erasable?
Yeah, for what? And just the thicker.
No, are they erasable?
The whiteboard markers.
It's heavy.
I don't know if you need them.
72. Oh, but anyway, I thank you so very much, my dear. You are very kind. Okay, now let's look at the extreme first. Do you understand what extreme means? Oh, so let's assume. Assume case one. VI, which is what? VGSN is equal to what? 0. Yes? Where? Can you show me where am I? This one is 0. Yes? What can you tell me about this? Oh, so the NMOS is off. Clear? No response. Clear?
Clear.
Oh, which means what? When I say the NMOS is off, what does it mean? By the way, is the PMOS on? PMOS is on. Clear?
Clear.
Yes or no?
Yes.
Okay, let's see if you can help. If PMOS is on and the NMOS is off, it means this one is what? Open circuit. Did you get it or not? Which means what? The equivalent is this. No. Are you following me or not? I claim this one is this. RDSP. I need you to understand what does that mean. In other words, what am I claiming? I am claiming that when you put VI equal to what? VGSN, I am claiming that the PMOS is going to be in which mode?
Triode.
Huh?
Triode.
Triode mode, which means what? It can be approximated by a what?
Resistor.
By a resistor. Did you get it or not? Oh, good. Now, but is there current?
No.
There is no current. Did you get it on? So even though the PMOS is on, but there is what? No current. Did you get it or not?
Yes.
Where am I? In this curve, in this curve. Where am I? Which one? Is it this or is it this? Huh? This one. Why? Just understand why. Look at the PMOS. Which region? Triode region. Yes or no? But is there current? No. But is it in the triode region? It is triode region, but there is no current. Did you get it or not? Yes or no? Good. What is the output voltage? This one is open now. This is open. What is the output voltage? Output voltage is what? VDD. Why? There is no voltage drop here. There is current, but the current is equal to what? Zero. Because it's the start of the what? The triode region. Clear? Clear? So what do I say? I say V0, sorry, PMOS is on which mode? Triode, but no what? But no current. Yes? No response. Yes?
Yep.
One more time. Can you show it to me in the graph? Where? Where? This one? Yes or no? I want you to look at the red. Look at the red. Are we in the triode region? Which is what? The beginning of the triode region. You agree? But there is no current. Why? Because the switch is open. Clear? What do I get? I get V output is equal to what? VDD. Which is what? VOH. Agree? Agree. Good or bad? Good. Remember the goal. What is the ultimate goal? I want VOL to be what?
Zero.
And VOH to be what? VDD. We say what? We have a full swing. Full swing from 0 to what? VDD. Clear so far? Yes or no? Okay. Can you tell me how do I get RDSP? How do I get the resistor? What did we say? The PMOS is which mode? Triode mode. What is the equation for the triode mode? IDP is equal Kp prime W over L P. Yes or no? Okay. What is the equation? Equation is what? Let's write the equation first of all, and then what? Substitute in terms of the V. It's what? Yes? Everything, all of this, by the way, is what? Is absolute values. Yes or no?
Yes.
Okay. And B, so. Clear? No response. Clear?
Clear.
Yes or no?
Yes.
Okay. Ignore this. Why ignore it?
Very small.
Why ignore it? It's very small. Did you follow me or not? It's very small. Clear? Why it is very small? Can you tell me, show me in the circuit why it is very small? What is the output voltage? VDD. What is this one? VDD. So the voltage between the drain and the source is what? Zero. Did you get it or not? Yes or no?
Yes.
Okay. So what is RDSP? RDSP, remember, it's the inverse of the slope. So RDSP is equal to what? I'm still waiting. 1 over, yes, Kp prime W over L P times what? What is VGSP? The input is what? 0, which means this one is 0. Yes? What is this one? VDD. What is VGSP? This one. 0 minus what? VDD, but I'm going to take the what? So what is it? VDD. Clear so far? Yes or no?
Yes.
Okay, one more time. What happened to this term? Ignore it. Clear? So, why is it 1 over? Because the slope of this one, the slope is what? Is 1 over the resistance. Yes or no?
Yep.
Question. Is this a large resistance or a very small resistance?
Small.
Very small resistance. By the way, is that good or bad?
Good.
That's good, because it means what? It means that when you drive, you can drive more what? More load with a small resistance. There will not be a large voltage drop across it. I'm not sure, did you get this point? Did you get this point? If the resistor, the output resistor is high, the voltage drop across it will be what? High, which means what? The input to the
Less voltage.
succeeding stages will become what? Lower and lower. We don't want that. Did you get it or not?
Yep.
Yes or no? Good. Now, did you understand this case? This extreme case. What is the other extreme case? Extreme case. Case 2. What is Vn? Vn equal to what? VGSN equal to what? VDD. Yes?
Yep.
VDD, high. Okay, help me. On or off? On. Why off? Can you tell me why off? Look at it. What is this voltage? VDD. What is this voltage? VDD. Which means the voltage difference between them is what? 0. But the voltage between them for the PMOS to operate, it has to be greater than what? Absolute value of VTP. You agree?
Yes.
0 is not greater than the absolute value of VTP. You losing me? Losing me? Okay, good. Clear? Okay, so what can you tell me? The NMOS is what?
On. And
The PMOS
off.
is off. V naught equal to what? 0, which is what? VOL. Clear?
Clear.
Why? Show it to me. Why is the output 0? Why? What is the equivalent circuit? What is the equivalent circuit for this case? This is the equivalent circuit. Agree?
Yep.
Agree?
Agree.
Which one is open now? The PMOS is open. Did you get it? Is there current?
No.
Where is it here? Can you show it to me here? Where am I? Huh? I'm here. Answer me the following question. I want you to look at the blue. Look at the blue. The blue NMOS or PMOS? NMOS. Which is it? What is it? Beginning of what? The beginning of the trial, but the current is what?
0.
0. Why the current is 0? Because PMOS is open. Did you get it or not? So what do I say? NMOS is on, beginning of trial. No current, but no current. So let's label this one. This here is case 1. This is what? Case 2. Clear so far? Oh, can you get me what is RDSN? RDSN. Exactly the same as what? As this one, but now it's what? For the NMOS. So, and no absolute value. Why no absolute value? For the NMOS, everything is what? Positive. Clear? So it's what? 1 O Kn. prime W over L N VDD minus what? VTN. By the way, again, what did I ignore? I ignored the what? I ignored the, sorry, I ignored the the square term. Did you get it or not? Yes or no?
Yes.
Oh, clear. These are the extreme cases. By the way, VOH is how much? VDD. VOL is how much?
0.
Good or bad?
Good.
Good. And answer me the following question. Is there power dissipation?
No.
Static power dissipation. I'm not talking about dynamic. Dynamic, we'll get to it. Static power means what? Remember, when you are dealing with digital logic, you have how many states? You have 0, you have 1, and you do have what? The dynamic, when the logic is switching from what? 0 to what? A 1. We are talking about the static right now. How much is the average static power dissipation?
0.
Why?
No current.
There is no, this one here is 0. Here is 0. So what? First one, advantages. 1, full swing. At output. Second, no power dissipation. Why is this one important? Because inside on the chip we are going to deploy what? We are going to fabricate millions and millions of what of these transistors. This one tells you what? There is no power dissipation or very little. Did you get it or not?
Yes.
Yes or no?
Yes.
Okay. By the way, what is the output resistance here?
Or
RDSN. Big or small?
Small.
Small. So in both cases, the input is what? Sorry, the output. Higher. Let's see if you still remember this. What does fan out mean? Did we discuss it in the introductory?
yes.
Fan out is what? How many logical gates can you drive? Did you get it or not? Because the output resistance is what? It's very low. The voltage drop across them will be very little, which means what? It does not affect the levels for the following stages. Clear? Now, I cannot say anything about noise margin right now. Can I?
No.
Why? Because I need for the noise margin, if you remember, which is very doubtful, noise margin, low, what was it? What was it? VIL minus what? VOL. What is VIL? One more time, verbally. What is it? It's the maximum input voltage that can be regarded as a what? Low. Did you get it? Oh. Where is it? Show it to me here. In the diagram. Remember, by the way, what is this? That's VTC, which means what? What is the axis? Don't look at my face. Don't look at my face. That's why I make copies for you. What is the x-axis? The in, and what is the output? The out. This is called VTC. This is called what? The IV characteristic. IV. Clear? No response. Clear? By the way, I don't want you to call it VI characteristic. It's IV characteristic. Did you ask yourself why did you put I in here rather than in here? Because the driver is the what? Is the voltage. In other words, the input is the voltage. The output is the what? Current. The output is always in the vertical. Did you understand or not?
Yep.
No response. Yes? Good. This is VTC. Where am I? Where am I? In other words, do you see the VIL? VIL is when the slope
-1.
negative. By the way, what happened? What am I doing to the input? I am increasing the input. Where did I start? At 0, which is which case? Vn equal to what? 0. Where was the operating point? Here. Did you get it or not?
Yes.
Now what am I going to do? I'm going to increase the input. Where am I going to move? I'm going to move through what? One of these. Losing me? Depending on how much am I increasing it. Clear? Listen to me. Let's assume this 1 volt, 2 volt, 3 volt. No, I'm looking at the wrong. Let's look at what the blue one. Yes, 1 volt, 2 volt, 3 volt, 4 volt. So when I increase the voltage, what am I moving? I am moving what? From here to here to here to here to here. Did you get it or not? But not on a what? Straight line. Not on a straight line. Clear? Okay, good. Now help me. I want you to look at the points between A and B. Yes? What does it tell you? Read it and tell me what does it tell you. Qn is in what? Saturation. But the Qp is in what?
Trial.
Where? Show it to me. I want you to show me that here in this diagram. Remember the extreme point. When B n equal to 0, when is B not? This point. So this case 1 is this one. Increase the what? Increase the input voltage. Yes? What can you tell me? Look at the diagram and tell me.
Rising side.
The NMOS is still what?
Trial.
Trial.
The NMOS. The NMOS is still what? Saturation. Did you get it or not?
Yeah.
But the PMOS is still what?
Trial.
Why? I started on the trial. Oh, it's on the trial. On the trial. I'm still on the trial. Did you get it?
Yep.
Yes or no?
Yes.
So how do I get the IL? The current is the same, but the mode is different, which means what? I need to equate the current in the triode mode for the PMOS with the what? With the current in the saturation mode of the NMOS. You lost me? Did you lose me? So what is it? Give it to me. So this is from where? A to B. Let's start with the NMOS. What is the NMOS? Which NMOS? What is the NMOS? NMOS is saturation. Yes? What is the equation? What goes in here? In the equation, in the original equation for the NMOS. VGS. But what is VGS? Huh? Input, which is what? VI minus what?
VT.
Close the bracket. Did you get it? No response. Did you get it?
Yeah.
Didn't I tell you to write these equations for the saturation and for the trial in a cue card? I told you to write it in a cue card to have it with you all the time. Now, do you agree that saturation for the NMOS?
Yep.
Now for the PMOS. Can you show me what is the what? The trial. I'm still waiting. I'm still waiting. 8. KP prime. W over L. P. Let's see if you can help me. What in the equation? What is it? It's BGSP, which is what? The voltage between this and this. One more time. VGSP. Yes? Which is what? This voltage minus this voltage. Did you get it or not? But I'm going to take the absolute value, which means what? It becomes what? VDD. Clear?
Clear.
No response. Clear? You lost me here. What was in the equation for the PMOS? The trial. What was it? VGSP. Yes? What is it? Look at the diagram and tell me, what is VGSP? is the voltage between what? The gate and the what? The source. Agree? What is the voltage at the gate? Vin. Yes? What is the voltage at the source? VDD. Which means what? It's Vn minus what? VDD. But Vn minus VDD is negative. Agree?
Yes.
I need to take the what?
Absolute value.
So it becomes what? VDD minus Vn. Clear?
Clear.
No response. Clear? Oh, what is the next one? Minus absolute value of what? VTP. Why? Because VTP is negative. Did you get it or not?
Yep.
Good. Next term. There are next term. What is it? It's what? It should be what? VDSP. Yes? And then what? Minus 1/2 VDSP squared. So this one is what? VDSP. Yes? What is VDSP? What is VDSP? I just wrote it here. Where is it? I erased it. Remember, VDSN is equal to what? Yes? Plus what? Agree?
Yes.
Agree? But what is VGSP? Is this minus this. You agree?
Yeah.
But this is larger than this. So what is this, by the way? That's V naught. Did you get it or no? Yes or no? So what is this? VDD? Because it's absolute value. Right? So it becomes like this. And this one, we are going to neglect it anyway. Clear? What do you get? You get an equation which has what? V naught in it and what? Vn in it. Clear? Do you see this Vn? Do you see this V naught? Yes? What do you do? You equate it equal to what? Negative 1. Yes? Yes? Now, let's take an approximation here. Assume transistors are symmetric. What does that mean when I say are symmetric? Kn prime W over L P, sorry, N is equal to what? Kp prime W over L P. Did you get it or not? Okay. Now, of course, you forgot. What is Kn prime? It's what? Mu N COX. Yes? What is mu N? Electron mobility. COX is the capacitance of the oxide, SiO2. Clear? Equal to what? SO times
Mu over L. P. No, it's
N is equal to what? Mu P COX
times
W over L P. Clear? Okay. Assume length of the channel is same. Which means what? L is the same. COX cancel, L cancels, and what do I end up with? Mu N over what? Mu P, yes, is equal to what? WP over what? WN. By the way, we are going to talk about sizing next week. So how do we size the transistors? Clear? How do we choose this W and the L? Did you get it or not? Okay. I want you to answer me the following question. Who is faster, electrons or the holes? Electrons are faster, which means what? Mu N is much faster than what? Mu P, which means what does it tell you about the width of the channel? The width of the channel of the PMOS needs to be what? Wider than the what? Than the width of the channel in the NMOS. Did you get it? For the two transistors to be what? Symmetric. Clear? Now, shortly, again next week, I will show you that the transistor being symmetric might not be the best solution Because remember, as you increase what? As you increase W, the width of the channel, you are going to use what? More space. Did you get it or not? Yes or no? And the capacitance also will change. Clear? But we'll talk about that shortly. Let's not worry about that. And also what? VTN is equal to what? No, sorry. I messed up. Minus VTP. Remember, VTP is negative. You agree?
Yes.
So when you multiply with negative, you get what? You get positive. Clear? Clear? If you use this approximation, this is the result that you will get. Taking derivative and so on and so forth, all of these things, you will get this result. One eight. 3 VDD plus 2 VT. Notice, by the way, I removed the subscript for the VT because they are equal. Did you get it or not? I assume they are equal. VTN and VTP are equal. Clear so far? No response. Clear so far? Good. I want you to see this result and go back to here. One more time. Where are we? We are at point what? B. Clear? The NMOS is what? What is the NMOS? Saturation. What is the PMOS? Trust. What do I do next? I increase the what? Input. Yes or no?
Yes.
Where? Show me where am I going to go? Going this way. You follow me or not? What would I reach? This region. You follow me or not? What can you tell me about this region?
They're both saturated.
They are both what? Saturated. Did you get it or not?
Yep.
They are, where is it here? Show it to me.
Vertical.
The vertical. QN and QP are both what? Saturated. Is the current the same? The current is the same. Do you follow me or not? So what do? I use what? This equation, and the other one is what? What do I put here? I'm still waiting. What is it supposed to be? VGSP. Yes? VGSP. What is it? VN minus what? VDD. But VN minus VDD is negative. I need to take absolute value. Clear? So what is it? Square. Clear? No response. Clear? Did I mess up? Did I mess up
This is
anything?
from B to C, right?
Say that again?
This is from B to C, right?
Probably what?
Based on, it's from B to C now.
From B to C. Yeah, from B to C. But I want you to tell me here, where am I? Where I'm keep increasing the input. Remember, the input is the blue. Yes? So I'm going where with it? I'm here right now. Yes? Is the red saturated?
Yes.
Is the blue saturated?
Yes.
Both of them are saturated. The current is the same. Did you get it or not? Yes or no?
Yep.
No response. Yes or no? Oh, I use the approximation. Yes? What? Sorry, I use the assumption. What is the assumption? The assumption is, help me. The assumption is that the two transistors are symmetric. Yes? Which parameter am I getting? Look at the diagram and tell me which parameter am I getting? VM, which is the what? Which is the inverter switching threshold. VM equal to what? VDD over 2. Yeah.
So from the region A to B and B to C, the left side of that.
From A to B, the region is what? Is saturated. The QP, sorry, the QN is saturated, but the QP is in the triode region.
Oh, I see.
This one now is what? Between B and C.
We're both saturated.
Both are saturated. Did you get it or not? Now, let's see if you still remember. Do you still remember the ideal inverter? How did it look like? Yes? And what was VIL? VIL was equal to what? The other one, VIH, which is equal to what? VM, which is equal to what? VDD over 2. Yes? Yes? Is this one exactly similar to this or no? This one is a little bit lower, the VIL. Do you see this VIL? Yes? No response. Yes? When will VIL be equal to VDD over 2? Look at the equation. This one should be what? 4. If this one should be 4 and this is non-existent, do you agree? Then what would this one be? 4 VDD over what? Which is what? VDD over 2. But this one is lower than what? 4 VDD. Why it is lower than 4 VDD? VT, this VT is around what? Around 0.5 volt. Yes? Times 2 is what? That's smaller than VDD. Did you get it or not? Yes or no? You can see it, by the way, in the graph. You see the VDD over 2? VIL is lower than it. Clear? In the ideal inverter, it is equal to. Clear? But VM, is it equal? The VM, do you see the VM? Where is it at? VM equal to what? VDD over 2. There also is VDD. Yes,
If they're not symmetric, is VM going to move up?
that is correct. And that I will show you shortly when we talk about the size. Clear? All what I try to tell you right now is the fault. It's that the fact that the transistors are symmetric might not be the what? The best solution. Did you get it or not? Might not be the best solution in terms of what? In terms, for example, on noise margin, in terms of the propagation delay, and so on and so forth. But let's finish with this one first. Clear? Okay, continue. Where am I going? Now between what C and D. Where, show me to me here. Where am I headed to? What am I increasing? I keep the increasing the what? The input. Yes? Which means what? I'm going this way. Yes or no? Hi. What can you tell me about the PMOS? Saturation. But the NMOS? Triode. Did you get it?
Yeah.
Lost me? Did you lose me? You keep increasing. By the way, remember the input is the blue one. Yes? It's VGSN. So as you move up, not along a straight line. Yes? Along these lines, and this is the load lines here. What am I going to reach? The red is what? The blue. That's this. That's between what? Between, help me, between point C and point what? D. QP is in saturation, QN is in the what? Triode region. What is the parameter that I need? I need VIH. Yes? What do? I equate the what? I equate the saturated current of who? Of the PMOS with the equation of the what? The triode current of the what? NMOS. I get an equation relating V naught with Vn. Clear? I take the derivative, I set it equal to what? -1. Did you get it or not? I get what? I get this result. VIH equal to what? Equal 1/8 5 VDD minus what? Minus 2 BT. Clear? No response. Clear? Yeah. Did you understand that, region? Did you answer where did we get this equation? Repeat it for me. How did I get this equation? What do I need to do? I need to take the current in what? In the PMOS, which is in saturation, and I need to equate it with the what? With the current of the NMOS in the triode. I will get an equation that has V naught in it and what? Vn in it. I take the derivative dV naught dVn. I set it equal to what? -1. I use the assumption that the two transistors are symmetric. This is the equation you get. Clear? Now one more region, which is what? From D to what? To the final point, E. Yes?
Yes.
What can you tell me?
PMOS is off.
Where? Show it to me. Can you show it to me? The PMOS is what? Off. By the way, what is the NMOS?
Fine.
NMOS is a triode, but what?
No.
No current. Yes? Where?
Case 2.
Case.
Huh?
Case 2.
Which is the extreme, I guess. Did you get it?
Yes.
Yes or no?
Yep.
Yes or no?
Yep.
Okay, and what did we do? The extreme case, which is what? The input is VDD. By the way, the input cannot be more than VDD. The highest value is what? VDD. Clear? What was the current? Sorry, what was the output voltage? 0, which is what? Which is sorry, not the output voltage, I'm sorry. The output voltage is what? VDD. And what do I say? The PMOS is what? The PMOS is off. The NMOS is on, triode, but no what? No current, because it's at this time. Clear?
Clear.
Okay, before your question, can you tell me what is the noise margin low and noise margin high? Noise margin low, which is what? VIL minus VOL, which is what? VOL is what? 0, and VIL is this. And what is the noise margin high?
OH minus VIH.
VDD minus this thing. Yes? I'll get your question in a minute. VDD, 5 VDD minus what? 2 VD. Clear?
Clear.
Okay. What's going on?
For
They should be equal. They are equal, sorry, I did not see this one. What is this? 3 VDD over what? 8. What is this? VDD minus 5 over 8 VDD. What is that? 3 VDD over 8. Agree?
Yes.
Second term is what? 2 BT over 8 plus. Second term is what? Plus 2 BT over 8. Clear? Which means what? The noise margin high is the same as the noise margin low. Clear? You lost me?
yeah.
Did you lose me? Yes, you did. Doesn't matter. Just tell me. Okay. Can we simplify this? VDD minus 5 over 8 VDD plus 2 VT over what? 8. VDD minus 5, 8 VDD is what? Agree? Which is what? Yes? Which is the same. By the way, I'll get your question. Did we expect it to be the same?
Yes.
Why? Because we assume that the transistors are what? Symmetric. If they are not symmetric, they will not be equal. Yes.
So from point 0 to A, that's case 1.
Yeah. The Q, what do I say? The QN is what? Of the QP is what? In the triode, but
No current.
no current. Where? One more time. Where? This one right there. Did you get it or not?
Yes.
Yes or no?
Yes.
Yes or no?
Yes.
Yes. This is the characters. Does it look good? Tell me, does it look good? By the way, the advantages because we have not calculated the noise margin. What do I say? High noise margin. Is that good or bad? When we say high noise margin, is that good or bad? To me, by the way, most important is what? There's no power dissipation. There is no power dissipation, which means what? Those CMOSs are not going to what? Gain heat. It becomes hot. You have to understand, on the chip we are going to have what? Millions and millions of these. So if there is power dissipation, the whole thing will become what? Hotter, hotter, hotter. There is no power dissipation. Clear? Clear the static analysis? This is static analysis. I did not bring propagation delay whatsoever. Now we go to the what? Dynamic analysis. Clear? So let's see if you can help me with the dynamic. Did you understand this? I want to get it over with. Everybody got it?
Yep.
Everybody? Okay, good. Now let's see what we have here. Clear? Help me. But before we get into that, can we go back to 350 or 240 or something? Let's see if we can help. Assume the capacitor is initially what? Uncharged. Yes? The input at t equal to 0 switch from from low to what? High. And then back to what? Low. Did you get it or not? Yes or no? Between two levels, extreme levels, 0 and what? VDD, for example. Clear? Tell me what happens. When this one goes up, what happens? The capacitor begins to what? Charge. You follow me or not? The capacitor begins to charge until it reaches what? The maximum value. Do you follow me or not? Can it reach the maximum value in 0 seconds? No, it cannot do that. Did you get it or not? These are what? These are electronic, cannot do that. Clear? Now, if you remember, which is very doubtful, V naught of T, the output voltage, is equal to what? The final voltage at the capacitor. What is the final voltage? After the capacitor charge to the maximum, what is it? It's VDD. Yes?
Yes.
Minus. Open the bracket. The final voltage. What is the final voltage? Final voltage across the capacitor is what? VDD minus the initial voltage. 0 times what? Do you remember this equation? We forgot. What is the tau? What do we call tau?
RC.
Time. Constant. And what is it equal to?
RC.
RC. Clear so far?
Yes.
No response. Clear so far? What is this? V of T. V naught of T is the voltage at the capacitor at any time. As T equal to 0. At T equal to 0, plug in the equation. T equal to 0. What do you get here? 1. What do you end up with? VD minus what? VDD, which is equal to what? 0. At T to infinity, as T approaches infinity, which means what? After a long period of time. Yes? What is T infinity? What is e to the minus infinity? 0. Which means what? What is the voltage across the capacitor? VDD. Did you get it or not? This 240. This 240, but even not what? It's not even 340 or 350. It's 240.
Right.
Clear?
Clear.
Do you remember how did we get this equation? We modeled the system as what? First order differential equation. We solved the differential equation. We find the roots, and the roots is what? E to the minus t over 2. Did you get it or not? Yes or no?
Yes.
Essentially, please. Oh, good. What does that tell you? It tells you, if you apply this, by the way, when we get to the CMOS, in just a second, what am I going to substitute here? VOH. Agree?
Green.
VOH. VOL. Are you following me or not?
Yes.
Yes or no? Oh, but we need to understand what is this all about and how do we calculate what is referred to as a propagation delay. Now, but first, you will tell me what? Professor, the circuit that you set or that you sketched for us, which I erased for the inverter. You told me what? Professor, I did not see any capacitor. Why? Because I was dealing with what? Static analysis. Static analysis is what? DC. The capacitor becomes what? A blocking capacitor. Are you following? It does not get into the picture. Clear? But right now I'm dealing with what? Dynamic analysis. Where are these capacitors comes from? Let's see. Inside the CMOS itself, inside the devices, there are parasitic capacitors. Do you understand what parasitic means? Parasitic means what? Remember those places when they create the enhanced channel and the what? And the gate, they create what is known as a what? As a capacitor when there is a depletion region between them. That's one. Second, wiring. That's why they always tell you when you implement or when you design your circuit, do not use what? Long wires. You follow me on that? You need to plan the layout very carefully such that you use as what? Short wires as possible. The longer the wires, the larger the capacity between them. Did you get? Wires are conductors. You agree? Air is a what? Insulator. So air between wires, you are creating a what? Capacitor. Did you get it or not? Yes or no? In addition, this inverter is going to drive other logical gates. Every logical gates also have a what? An input capacitor. Did you follow me or not? The input capacitor of those gates will be what? Will be regarded as load of the what? Of the driver. Did you get it or not? Yes or no?
Yes.
Question. The higher the fan out, the higher the fan, remember the fan out? What is the fan out? How many what? How many gates are you driving? The higher will the capacitor become higher.
Yes.
Why?
More wires.
No,
Capacitors
that
in
has
parallel.
nothing to do with the wire. We already talked about the wires. Now we are, yes,
Is the capacitors in parallel?
very good. The capacitors will be in parallel. And when you have capacitors in parallel, the overall capacitor will be higher or lower? Higher. Because capacitors in parallel, when you find the equivalent, you treat them as what? As resistor in series. 240, 240. Do you remember?
Yes.
It becomes higher and higher. So the more gates that you what? The more gates that you drive, the input capacitor of each one of these gates will be in parallel, resulting in what? Higher capacitor. Now, how are we going to model it? I'm going to group all of these capacitors from wires, from what? From parasitic, from what? The fan out, and I'm going to represent it by what? By a capacitor like this. Did you get it? No response. Yes or no?
Yes.
Yes or no?
Yes.
Yes or no?
Yes.
I'm grouping all the capacitors. I'm calling it what? C. Now, next time we will break it into multiple components. But for time being, it's C. Clear so far? Now, let's see what will happen here. Assume the input is what? Low. The input is low. What will happen?
Charge.
What can you tell me about the NMOS?
Charge. Oh,
It's on.
Huh?
Off.
Oh, PMOS.
on.
On.
What happened to the capacitor?
Charge.
Begin to what? Charge to where? VDD. Did you get it or not?
Yes.
Yes or no?
Yes.
Okay. The input suddenly became what? High. Yes?
Yes.
Yes?
Yep.
Yes?
Yes.
Help me. What happens?
Takes time to.
The NMOS becomes what? On. The PMOS becomes what?
Off.
What happened to the voltage across the capacitor?
Discharges.
Discharge to where?
Ground.
To the ground. Did you get it?
Yep.
Yes or no?
Yes.
The characteristics is like this. Where is the B not? Where's the B? What is it? The N of. I'm still waiting. What is it here? Here. What is the input here? Is the input zero? Yes? What can you tell me about the NMOS? PMOS? Capacitor already what? Charged to BDD. Yes? By the way, what am I assuming? That this one was what? Was low for a long period of time. Yes?
Yeah.
Which means what? What am I starting? BDD. Did you get it or not? No response. Did you get it or not?
Yes.
Yeah.
At the time, at this time, what happened? The input became what? High. The NMOS is turned what? On. PMOS is turned what? Capacitor begins to what? The charge to where?
Ground.
Show them. Clear so far? No response. Clear so far? What happened here? The input went what? High again. Sorry, low again. Yes? What can you tell me about the PMOS? On and MOS? What happened to the capacitor? Began to charge. Yes?
Yes.
Clear so far?
Clear.
Okay. What is this VDD? When you reach VDD over 2, yes? Yes? This is called what? TPHL. What is TPHL? Propagation delay. Why is a propagation delay important? Why? What is it a measure of?
Response time.
Huh?
Response.
I understand what I'm saying, that why do I want the propagation delay to be what? Low. Why? I want the device to be fast. The speed. The whole thing is about the speed. Propagation delay is related to the what? To the speed. The low propagation delay means what? The faster the inverter is. Did you get it or not? Okay, good. This, what is the HL? High to low. Propagation delay, high to what? Clear? Can you show me where is the low to high? Where in the diagram? Going from here to where? Which is VDD over 2. This. TPLH. Clear so far? No response. Clear so far?
Clear.
Question. Do they have to be equal? No, they don't have to be equal. By the way, if the transistors are symmetric, they will be equal. But if the transistors are not symmetric, they will not be equal. So how do we calculate the propagation delay? We take the average. Did you get it or not? We take the average. In other words, the average propagation delay is what? Clear?
Clear.
No response. Clear?
Clear.
Okay. By the way, if they happen to be equal, then it will be the same as of either one of them. Did you get it or not? If you are adding two, in other words, if this is equal to this, then the overall propagation delay will be either one of them. So how do I define the propagation delay? The propagation delay. Let's say, for example, HL is the time it takes for the output capacitor to discharge to what? To VDD over 2. Clear?
Clear.
No response. Clear?
Clear.
Oh, and the same thing, by the way, for the charging. How long does it take to charge what? VDD over 2. Clear so far? Answer me the following question. If I'm using a resistively loaded inverter, resistively, not the CMOS, yes? How do I calculate this? By the way, if it is resistively loaded, is this correct? God, we just started. Oh my God. How will the capacitor charge?
RC.
Through R. You follow me or not? Which is what? This is not a ground, sorry, BDD. Yes or no? Which means what? Does it look like this?
Yes.
That's the input VDD. Yes? Resistor is this. And then what? Ground. Because this one will be what? Open. When the capacitor charge, it means what? It means the input is what? Low. The NMOS is off. Agree? How do I calculate the propagation delay? Which equation do I use? I use this equation, yes? But what do I plug? In here, I plug what? BDD over what? 2, yes? And what is the unknown? You lost me here totally. You lost me totally. Did you lose me? Admit it. Tell me the truth. I can handle the truth. Can we try it one more time? Have mercy on me. This is the first class. Have mercy on me. The resistively loaded. Yes? Yes? When will the capacitors charge? When the input is what? Low. Do you agree? When the input is low, what can you tell me about the NMOS? Oh, which means the capacitor is going to charge. Yes? Yes? To what value? VDD. But I don't want it to charge to what VDD. Because when you calculate the propagation delay, all what I need is what? To calculate how long does it take it to reach what? VDD over what? 2. Look at the definition. Clear? So what do? I see this equation. Yes? I plug in what? VDD over 2 here. Yes? Yes? What is the unknown? T. That T is the what? Is the propagation delay. Which is what? The propagation delay. What is it? Low to high or high to low? Low to high. Did you get it? Plug in here. VDD. You got this one. Did you get it? Yes or no?
Yes.
Next time we'll do the analysis. Oh my God. Did you get it? By the way, if you do not read the book with me, you are doomed. You believe me, I say. There is, listen to me. Am I with you when you go home? Yes, I'm not with you. But I bet my life you do not open the book till the class comes. And you just come to the class. I bet my life. Is that true or not? Be honest with me. Which means what? In the book. In the weekend. Do you open the book? Be honest with me. Be honest with me. Do you open the book? Do you review the notes? You are doomed. You are doomed. By the way, what did I tell you at the beginning of the semester? Is this an easy class or hard class? Hard. By the way, have I ever been dishonest with my students? No. I always tell them at the beginning, what did I say for 455? I told you it's an easy course. This one, I told you it's a very hard. But if you are just if you think that just coming to the class is enough, think again. Think again. But I saved my piece. So if you want, fine. If you don't want, I will see you next semester. Do you want that? You tell me. Do you want that? You want to graduate as soon as possible to get opportunities to work to make some money? Enough of what? Going to mom and dad, tell them what, please, I love you, give me money. Enough of that. You need to know, you need to learn how to stand on your feet. Okay, go home, go home.